So I set this up, I'm going to slide in again, give you a lecture before lunch, and then toss the ball to Professor Kramer to give a lecture after lunch. I want to pontificate. If I sound like I'm a preacher sometimes, this will be my most preachy lecture because I firmly believe nothing is more important than how you sample the soil and how you test it. All the fancy analysis you do is no better than the site investigation. When I have a student doing another study in New Zealand, I flew out with her and we did the sampling together. After training her in the U.S., I want to be there when she's doing her testing, even though she's a very capable person. And then when she starts her laboratory testing, I want to be there. And then I sent Professor Reamer from Berkeley to spend 2 weeks with her in New Zealand to make sure he was comfortable with everything that the lab test device was doing. And now she's working away and she's sending me WhatsApp photographs of specimens and we're interacting, but nothing is more important than having a good understanding of the quality and the limitations of your laboratory testing, which is based on your site investigation. In many ways, we know as geotechnical engineers, our job is to find these buried stream channels that re-emerge during an earthquake event. This is a buried stream channel that re-emerged because of liquefaction and ejecta after the 89 Loma Prieta earthquake. It always starts with geology. I like to complement that with geophysics. I'm going to spend most of my time talking about the geotechnical tools. We're all a product of our experience. I had worked in the Mississippi area and I had worked in Turkey, in Al-Mazari, which is a lot like the Mississippi with a meandering river and slow streams. So I was thinking of that in my fluvial environment. It took me a while to step back and look at this photograph and realize the Southern Alps in New Zealand are just being pushed out of the ocean. And then as the rain, which hits these mountains, goes to the Pacific Ocean, they're not Mississippi meandering rivers, they're like fire hoses. And so finally I realized, okay, I've got to change my brain around because this is a different depositional environment. There are a lot of buried stream channels that were mapped by the geologists in 1850 when they were just starting to develop the city of Christchurch. These maps are available. I didn't know about them initially, but after looking at that, all of these buried stream channels are covered up because they just covered the area up. But those areas where there was buried stream channels were the areas where we had liquefaction during the Christchurch earthquake. There's a book I found called Christchurch, Swamp to City. If you can, get old photographs, get historical documents, and look at what the ground looked like before we messed it all up, before we buried things. There's actually a little place in Christchurch that has preserved the history of the environment. And I went there, and I was very proud, because I spent time walking around this park and seeing what Christchurch used to look like. So I have that in my brain as I walk the streets of Christchurch, and I know what's underneath those streets. And Bishio told me, Professor Ishihara, when he came here, he found that little park, and he spent as much time as you did walking around that little park. So don't do it because of me. Do it because Professor Ishihara says it's the right thing to do. When you go to a new location, find a place that has not been disturbed by humans and see the geology the way it is, and then understand that and translate it. Here's a location where I had a building I was investigating. There was a parking lot next to it, and right away I realized, okay, ground conditions vary tremendously over short distances, and the stream is shown going here, and it stopped here, but I think there's a liquefaction feature here, so I'm going to do closely spaced CPTs across that parking lot. So here's, you can see the area of severe liquefaction. You can see some of the ejecta. Here's my closely spaced CPTs. I'll later see how it interacts with this building. Here's the cross section. Where there was no to minor liquefaction, you push the cone and it actually hit refusal, or it hit dense soils and then medium dense soils and dense soils. Where it found loose, saturated, silty sands and low plasticity silts, looks like a buried stream channel to me, is where we had the liquefaction. So the geologic maps that were done in 1850 before the city of Christchurch was built were invaluable and then confirmed by these closely spaced CPTs. Besides the streams, there are these backwater areas of overbank deposits of siltier and clayer materials, which are the true swamps of Christchurch. They're persistent. I first thought they can't be persistent because the water's meandering through there, but these are like fire hoses that stay in the same location. And so we actually did CPTs and borings that showed the upper 5 meters of these materials are essentially the same thing. So what the black maps mapped as swamps in 1850 were swamps in 1,000 year, and were swamps 2,000 years ago. And this is what they look like when they chopped all the trees down and put fill on top of them. And this is what we see with careful sampling. We see this layering, which is a very different geology than a clean sand. Geophysical methods are useful because without a borehole, we can get global measurements of the shear wave velocity profile. The preferred technique is the multi-channel analysis of surface waves. You get more sensors and you get more information, so you have a little bit more reliability in getting the dispersion curve, which gives you the shear wave velocity profile from the Rayleigh waves. I also like suspension logging because I can go to whatever depth I want and I get local measurements. I get what is the shear wave velocity of the layer between the two receivers that Professor Kramer talked about. Although I like these local measurements, when I see variations like this, I do not want to model these variations in deep soil or shade. Because remember, earthquake waves are 100 meters long. They don't see little bands like that. And in a program, what can happen is if you have a soft layer between two stiff layers, when the earthquake comes through the first iteration, the soft layer gets softer because it strains. And because it strains, it gets softer. And because it strains, it gets softer. And then you have this thing where everything that's base isolated is sucked up into these little layers. It's like the cream filling between your dessert bagel or whatever. Okay? So step back and don't use too many layers. Look at the big pictures. Look at it like the earthquake looks at it. And then probably the most practical technique is the seismic CPT, because you're going to do the CPT anyway, so why not on some of them put the two receivers behind the cone and do the test. You do the test in one direction and in another direction so you get these butterfly loops. I like to look at the time between zero crossings. There are correlation functions, there's first arrival, there's other ways of looking at this, but it's a much clearer definition of shear wave velocity if you have two receivers and you can look at the arrival time between the upper and lower receiver. I trust those more. I never do a measurement unless I already know what the answer is. The first time I did seismic cone, I knew the shear wave velocity in the Young Bay mud was going to be a certain value. The test results came back from one of the leading contractors, and they were about 2.5 times greater than what I knew they should be. So I called him up on the phone and I said, when's the last time the device was calibrated? Oh, it's been a year. You know, ASTM says 6 months. Would you mind calibrating it again? Oh, begrudgingly he did. And 3 days later he called me on the phone. Even though I could not see him, this was 1990, so these were the days where we didn't have cell phones, I could feel the sweat coming down his forehead. He goes, take every value I gave you and divide it by 2.38. I go, okay. If I hadn't known what the answer was, I wouldn't have known that he had a mistake in his calibration. So I give you some shear wave velocity correlations for cone. They're number one, so at the top. Begrudgingly, because I hear some of you do SPT, here's some shear wave velocity correlations for SPT. And there are site-specific ones, but at least you have an idea of what the shear wave velocity might be before you measure it. But measure it. The other value to doing the surface wave techniques is they typically give you P wave velocity. I guess you could get this from the other techniques as well. In fact, you get it from the suspension logging as well. And what that tells you is the depth to full saturation. What I have learned, and Ken Stokey has actually said he's seen this on several other sites, is when you're in areas with tidal fluctuations, the highest height of the water, everything is not saturated below that. If the water is going up and down, it doesn't have enough time to saturate that material, and so actually the depth to full saturation is often a meter, sometimes even more than a meter, below what you consider to be the groundwater level. This will not liquefy. So we can reduce conservatism if we use a liquefaction analysis that only looks at the soil that will be saturated when the earthquake hits. The cone penetration test is the preferred way of investigating the site because it's electronic, it's standardized, you get the tip resistance, QC is measured. We want to take that measurement because the cone actually has an interior rod and then it has the full cone, so there's an unbalanced water pressure. We would hope that the cone would be built so that it has an area ratio of 0.8 or greater. Some of the older cones have low area ratios. You don't want that because the bigger the area ratio, the smaller the area ratio, the bigger this correction. You don't want to have to make a big correction. So use a cone operator who has a modern cone that has an area ratio greater than 0.8. Then this is a smaller value because it's 1 minus 0.8 or higher. But if you take the measured pore pressure times that difference in the area to correct what you measure to get what is actually called the corrective measurement. This is the correct measurement. This is wrong. We know it's wrong because of the unbalanced water pressure, so we use QT. Now, a lot of people just say QC, and like you'll see a lot of things we talk about today, they'll say QC. When they say QC, they mean QT. QT. Not so important for clean sands, because they have high tip resistances compared to the water pressure, but for silty soils, and especially for soft clays, you want to make sure you do this tip correction. You get the sleeve friction, and of course you get the water pressure. And you get a nearly continuous record of this as you push it to the ground. Now, most cones have robust strain gauges and proper load cells, such that with a typical 20-ton cone, the full-scale output is equivalent to a QT or QC of 100 megapascals. Since their accuracy is within 0.1% of the full-scale output, that means their accuracy is plus or minus 0.1 megapascal. Typically, clean sands, even if loose, have a QC or QT greater than 10. So that means with plus or minus 0.1 megapascal, your accuracy is better than 1% of the measured value. However, if you're pushing a cone in soft clay and you use a typical 20-ton cone, now your accuracy might be your accuracy would be worse than 10%. So if you're saying the strength of this material is 20 kPa, or 25 kPa, or 40 kPa, you could be off by a factor where you say it's 40, but it's actually more like 45 or 35. So what that means is you should measure your profile first with a 20-ton cone to realize when the soft clay stops. But then the rest of the investigations should be run with a 5-ton cone so that the accuracy is better and you get a more reliable tip resistance, so therefore you get a more reliable estimate of the undrained strength of that clay. Always make sure you do zero loadings before and after each CPT to check whether the strain gauge has been damaged during the testing. Don't accept working with a cone operator who doesn't give you their calibration chart, so you know when the cone was calibrated, and they give you your zero balance readings before and after each cone is pushed. If everything's done well, and it normally is, and you check those things, then the cone is very reliable. Now, Robertson and Ride, and then Robertson 2009, recognize you should be using normalized properties because everything in the world is stress dependent. If I have a soil with a relative density of 50% and I push the cone in at a depth where the vertical effective stress is 100 kPa, I'll get a certain tip resistance. As I push steeper in that same soil with exactly the same relative density, I'll get a higher tip resistance. So I'm going to correct everything back so I can get a normalized tip resistance and bring everything back to what it would have been at a vertical effective stress of about 1 atmosphere, or 101 kPa. We used to say clean sand, this exponent for this correction was 0.5, 0.7 for a silt, 1 for a clay. As we've learned, we realize it's a function of the soil behavior. So we're going to talk about a soil behavior type index to make this N value. So the N value is going to go anywhere from maybe 0.4 to 0.45, mainly around 0.5, 0.45, 0.55, and then maybe be 0.56, 0.7, and then eventually get up to maybe 0.8 to 1. That correction is made to our total tip resistance corrected minus the total vertical stress, normalized by the atmospheric pressure, so this is dimensionless, times Cn gives us a normalized, corrected tip resistance, or a big Q. We should normalize sleeve friction and tip resistance, but we're going to normalize them by the same thing, so we can just take the sleeve friction and divide it by the tip resistance difference to get our normalized friction ratio, or the VF. Robertson, working with, or building on the work that was done actually by Dean and Jeffries, recognized he could look at this normalized tip resistance that goes from 1 to 1,000 on a log scale, and he could look at this normalized friction ratio that goes from 0.1 to 10 on a log scale, and he could draw, there's some center of a circle over here. This is the equation for a circle, or the radius of the circle. You can see that you can divide the world into different zones. These are more kind of gravel or sandy gravels, sands, silty sand mixtures, clays, higher plasticity clays. You get some response due to higher OCR. You have a place in here where you have increased sensitivity of the clayey soils. You have a zone here where it's, all things being equal, increasing density. Soil behavior type index is far better than the unified soil classification system. Taking a disturbed specimen and running it through a sieve, doing things even like water contents, gives you an index of different types of soil that we then correlate to different engineering properties. This is measuring how this cone is pushing into this clay or this sand, and it's basically being compressed and being sheared. It's giving us an index of the type of soil behavior. If you gave me a choice and you say, I'd rather know what the unified classification was, or I'd actually want a physical test that tells me how the soil is responding to something being pushed into it, I want the direct measurement of the cone penetration test. I want to know the soil behavior type index. If the soil behavior type index suggests it is a dense sand, and you actually see it's a heavily over-consolidated clayey silt, it's just saying a heavily over-consolidated clayey silt acts like a dense sand. As far as in terms of behavior types, they're the same. In terms of unified soil classification system, they're different. But the unifying factor is the response of the soil, the index of the type of soil behavior. And so it's invaluable to look at the normalized tip resistance. You can correlate that to relative density in a more robust way with a cone correlation. And then you can get this I sub C to give you a sense of how the soil is responding to this penetration test. Always do cones first if you're going to do a boring. When I was in Advisory, I go, okay, high friction ratio, that's more clay. I have low tip resistances, that indicates more of a clayey material. This is getting up, the friction ratio is going down, this might be silty. So I know that, so then I go maybe 2 meters away, and I do my sampling, and I deliberately sample that specimen, or that layer. And that's what we did to get the blow count of 7, and you get the actual characteristics to classify that soil. If you do borings first, you don't know what you're looking for. If you take samples every meter or every meter and a half, you don't know what you're looking for. You should have an idea of what the soil looks like, and then you should strategically sample close intervals where you want soil, big intervals where you don't want soil, so that you're getting the most for your money in the investment of a soil investigation program with a boring and sampling. Some people say, well, I want to see the soil. Modern cone rigs have this device where you can push the cone, and then you see a soil that's kind of interesting. You can just go maybe a half a meter away because you don't worry about disturbance here, and you push this hydraulic piston sampler down with the cone device, and you get the soil. You can do sieve analysis, you can do water content, you can do Atterburn limits. You can do everything you would do with an SPT sample, which is disturbed as well. So I've done projects where I have not mobilized a drill rig. Everything's been done with the cone, geology, maybe some geophysics and cone, and then I've taken some samples with this device so I can see some of those soils that I want to see. It's less expensive than mobilizing 2 rigs. Robertson, and I have this paper given to you, updated this in 2016 in a paper that's well worth reading, because I think he moved one step further to what we really care about, and that is the soil clay-like or is it sand-like? And I've been arguing with him for years that there's not black and there's white. There's always black, gray, and white. Okay? I'm a big believer not to say one or the other in a dividing line, but to go this and that and something in between. So he has that. He has this transitional soil between sands and clay-like. Moreover, notice the D here. These are sand-like dilative, transitional dilative, clay-like dilative. That's what you care about. You care about whether the soil would want to dilate or contract in drain shear. And this is very scary because this is clay-like, contractive, and sensitive. The dividing line between dilative and clay-like is drawn as a line of 70. I said, Peter, you listen to me here, but so then you drew this dotted line in right here. Okay, maybe I should have put this dotted line in too. I think there should be a transition between the two, because you don't go magically from clay-like, from contracted to dilative on a line like that. So see a shade of gray here too. But at least if you have a soil up here, you know it's sand-like dilative. If you have a soil here, it's clay-like contractive. And so it's a very good way of looking at the index of the soil, the response of it. As much as I like the clay, the cone, and you get measurements every 2 centimeters, you're not capturing the soil of 2 centimeter thick layers. Recognize that a cone is a penetration device, and if the soil is contractive, maybe it's sensing an area that's 2 times the cone diameter. If it's highly dilative, because it dilates against the applied shears of the cone going into it, maybe it goes out 15 times the cone diameter. If I take a typical 10 centimeter square cone, although I prefer the 15 centimeter square cone, because with the bigger cone, followed by the smaller rod, you can go deeper. People think that you get to refusal because of a high tip resistance. That's not true. You typically hit refusal because of all that shaft friction along the cone rod. So having a bigger cone followed by a smaller diameter rod gives you a more robust cone that's less likely to break if it hits a piece of gravel, and you get deeper because you have less friction. That little bump that some people put on the cone doesn't work well. The friction reducer. The hope of a friction reducer. So for a typical 10 centimeter square cone, taking a typical number like 5 times the cone diameter, you are sensing a zone of soil that is slightly down below the cone, but we'll put it at the cone depth. It's compressing this material, it's shearing this material, it's riding up over here. Typically, it's 2 centimeter measurements of each 18 centimeter thickness of cone, of soil. That's better than the SPT. The SPT is bigger in diameter, and it's dynamic, and it's destructive, and it's actually measuring an area that's probably 20 to 30 centimeters. Because the cone is seeing ahead of itself as well as seeing the soil it's at, you could go from a clay to a sand, and because it's seeing the sand a little bit ahead of it, and then is still feeling the clay while it's in the sand, you would actually say there's a silt here. So if you transition from a clay to a sand, that's a good place to take a sample and prove to yourself there is no silt. The ice of sea is transitioning over, and it's saying there's a silt there, but it does not exist. It's just the error of the scale effect of the cone looking out in front of it. There are ways to remove these transition zones. So Peter Robertson has a way to do that within CLIC, a very popular program. And you can turn them off and turn them on, and you can check with soil sampling to confirm that it's not there or not. Or Ross Boulanger and Jason Young from UC Davis developed a way to do this, and actually Peter, being the gregarious person that he is, immediately implemented, right after it was published in CPT 18, into CLIC. There's also the other way of looking at it. If I push into a sand from a clay layer, it takes a while before I recognize I'm in that sand. And if the layer's not that thick, it all of a sudden sees the clay below it, and it doesn't get up to the proper resistance that it would have if it was just a thick sand layer. So we call that the thin layer correction. You are measuring a tip resistance when converted to a relative density or a QC1N clean sand equivalent, that is too low because it's actually seeing the soft clay when the cone is at this depth. I always apply this thin layer correction because it's conservative to do so. I mean, it's conservative to do so because from all the studies that have been done, this equation that's in Yaddo 2001 is kind of a lower bound to what it really is. I'm hoping that over the next few years with research, we will move away from this really conservative thin layer correction and do a better job of correcting it. But it's reasonable to be conservative given some of the uncertainties. Always stop while you're doing a cone and do pore pressure dissipation tests. Remember, liquefaction, especially the redistribution of pore pressures, is as much a fluid mechanics problem as it is a solid mechanics problem. And it doesn't cost that much while you're stopping to change the rods, to just stop and let the pore pressures dissipate, measure that, and calculate the radial consolidation, which can be turned into a horizontal hydraulic conductivity, which with some assumptions can be changed into a vertical hydraulic conductivity. At least you have something that captures the hydraulic conductivity of the soil. And that's going to be important for an effective stress analysis. Plus, it confirms where the water table is. And then sometimes it shows you actually have artesian conditions. You thought you had hydrostatic water pressures, but by stopping and measuring the excess pore pressure and how it decays and getting to the actual measured water pressures, you find out it's higher than hydrostatic. And you've got some aquifer charging your soil layer from below. Now people say, well, I can't use a cone here because I have gravels. I can't get the cone through gravel. I pushed, actually my student went over there, was very depressed. Out of the first 12 cones he pushed, he hit refusal in all 11 in this shallow, dense gravel. I got with the contractor, and he came up with a brilliant idea. He said, here's what I'll do. I'll push the cone until I hit refusal. Then I will pull the cone out and drive a collar with a dummy cone. This is a dummy cone. And I will just ratchet that down until I can feel like it's given. Then I'll pull the dummy cone out of the pre-collar system, and I will push my regular cone back in. With that new system at exactly the same site, hit refusal, push the dummy cone through, pull the dummy cone out, and then continue along the way. So without a drill rig and having to stop, move off, drill down, move anything back, this one device, and it's explained in CPT 14, which is a paper I've given you, is that it can get to any depth you want. There's also just being lucky and being aggressive. Most cone operators don't like to go to tip resistances greater than about 40 megapascal. But I'm a professor. I said I'm going to publish your work. I'm going to make you famous. I'm also crazy enough to buy your cone if I break it. I've never bought a cone. So good to be lucky. Plus, mainly when you push the gravels, it's not resistance that gets you, it's inclination. You just happen to hit a piece of gravel and went the wrong direction. If you go just 1.5 meters over, you're not likely to be unlucky again. If you are always unlucky, then you need to reevaluate your life. Okay? So we got Kruger out with a bigger truck. They're from Australia, and Australians like to compete with New Zealand people. So this thing got beyond 80 megapascals. Okay, we almost maxed this cone out, but we got through it. So obviously, being aggressive and lucky is another way to go. For gravity soils, probably one of the better techniques is the Becker hammer. But the Becker hammer that's not instrumented is unknown. So if you are going to do the Becker, you're going to go through all the expense of that for a critical dam project, you need to get a hold of Jason Dion and look at strain gauges that are at the bottom because trying to figure out the friction along that device is really difficult. So even measuring the energy at the top with strain gauges and accelerometers is not good enough. You want to know the energy at the tip, and then you have a hope of making sense of the Becker. Other than Jason DeYoung and maybe Les Harder, I don't ever trust the Becker hammer. The diesel hammer, all the issues, all the errors of energy, I've never trusted it. A large penetration device to me is less expensive than the Becker, and if it's been calibrated, plain sand and the gravels, that might be your way to go. Another thing you can do is push the SPT or a large sampler into the gravel, and when all of a sudden it just jumps up, ignore that and just extrapolate down and say, oh, I hit the gravel piece. I don't care about gravels. The gravels are floating in the matrix of sand. I want to get the SPT of the same sand matrix. So that's another way of going. I've blotted out the contractor. I have never used SPT data in New Zealand. With all the practice and research I've done in New Zealand, and I think there's over 4,000 borings with SPT. I've used the borings because they give me information on soil. I've never used the SPTs. Why? I have no idea how they measure those SPTs. I don't know if they used a one-nut hammer, whether they used a donut hammer, a safety hammer, 2 wraps around the cat head, where they pulled it 30 inches and dropped it. I don't know all those things. Most people don't document it. And then, if I care about something, I must measure it. If you as an engineer are going to use an SPT end value in your calculations, if you're going to decide between site's going to liquefy, it's not going to liquefy, you have to measure the energy. That's the biggest uncertainty with the SPT. I have measured energy on systems that people swore, this gives you 82% energy. I've measured energies of 30%. I have measured energies of 108%. There was a system that actually pushed on the rod to lift the hammer, and so I was actually getting a boom, 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 and the total integrated energy was 108%. I do not trust anyone with energy. I measure the energy. And it's not difficult with something like the SPT analyzer. You can make this on your own. It's just 2 accelerometers and 2 strain gauges. You have an elastic rod, so the strain gauges basically give you force. Integrating the acceleration gives you velocity. Force times velocity gives you energy. So blow by blow, you know the energy. When I first did this in Turkey, and I brought the devices over, I was measuring 30 to 80% energy. I go, this is not good. I'm a professor from Berkeley. I will not stand for this. And I said, you have got to mark the rod. You've got to carefully look at this. After a couple of days, the man became a machine. I showed him a little box. I said, that number, I want that number to be 60. I'll accept 55, and I'll accept 65. But I want 60% energy blow by blow by blow. And that's what I got. Now, a better system than a human being being pushed to their wit's end by a professor is an automatic trip hammer. Most automatic trip hammers are set for 82% energy, or 80% energy. Reset them so they give you 60% energy. Because we know there's no way this is linear. I don't want to correct energy. I want the system to deliver 60% energy so that I get an N60 number without having to do a correction. If you measure the energy, you know the dispersion of your energy, and you know the median value, and you don't have to use Skempton correction factors that were done in 1986 that actually I found work well for loose soils, but do not work well for denser soils. So I can reduce conservatism and not apply the short rod correction, because I know the energy being delivered blow by blow. Last but not least, if you haven't seen it yet, you will see the sonic boring. Why? It's continuous and it's cheap. Has anyone seen the sonic board in Columbia? Okay. What? Next week you're going to see it. Okay. When you have a chance to see it, stand next to it while it's going down. Then they pull it out and do an SPT. You have just densified the soil. I can feel the vibration. I can feel the earth move under my feet while they're doing the test. It's okay for continuous sampling. It gives you the soil. It looks a bit messed up, but you can't use SPT and sonic borings together. You get what you pay for. This is what I love to see. I have become a big believer in going back to the past and doing continuous, careful, undisturbed sampling, and then logging the holes with a geologist, like the beauty that it is, to look at layering. So I see layering here at a site that did not liquefy. I don't see the same layering of silts and clays and organic material in this site that did liquefy. The cone and the SPT and everything says both these sites are the same. But my eyes, since I now can look at them, tells me they're different. Much of this is to calibrate constituent models. And so I do believe in sampling to get soil specimens, if I can get them undisturbed, because I know as much as I love the PM4 sand and PM4 silt models, they're great models, and they give you only need 3 parameters, and you can just trust them for the rest of the parameters. I like to actually look at changing some of those secondary parameters to get a better calibration. And I can only do that with site-specific laboratory testing. So beyond the shear wave velocity in the cone, which can largely give you the 3 parameters you need for this model, I like to do advanced testing for the other parameters. Not all of them, there's like 22 total, but there's a few other ones I like to look at, like strain accumulation after liquefaction. And so, my favorite sampler, I've traveled the world, I've seen different samplers. My favorite sampler is the Dames & Moore hydraulic piston sampler. I know that to be true because I bought one. The person I worked for at Dames & Moore, he bought his own that he has in his garage. When I did my work in Turkey, I shipped my cone, my Dames & Moore hydraulic piston sampler to Turkey and did all my testing with the Dames & Moore hydraulic piston sampler. I originally started with this NGI device that was wonderful. It was not. Nothing beats the Dames & Moore hydraulic piston sampler, other than maybe the Laval sampler in a really soft clay. Okay, so if you really, really want to do undisturbed sampling of a highly sensitive clay, I will concede to the Laval sampler. But that's more difficult to run and more expensive. Dames & Moore is probably good enough. I treat my soil samples better than I treat my kids. So my soil samples are less disturbed than my children. Because I need these soil samples to preserve what they have in the field, to do the consulting, to pay for the money to send my kids to college. That's the way I explain this care I take. Dad, you care more about soil than you care about me. And then I always push the soil out the same way it went into the tube. These details matter. Stress reversals are bad. So if you push the soil in, if the soil goes into the tube this way and then you push it out that way, you've done a stress reversal. I like to use stiffening rods and carefully cut the rod because the least amount I have to push out of the soil, the least disturbance. I am a difficult person when it comes to laboratory testing. But you know the good thing about that? I once was walking through a lab and this person was complaining about this blankety blank. We had all these little rules about, I want you to measure the void ratio upon reconsolidation. This. The tests he did for me, same price, were the best tests he'd ever done. So you only get what you ask for. Without being incredibly rude, you want to push people to do the best they can do with their testing device. The difficult thing about disturbance is I can prove when my samples or other samples are disturbed. Like shear wave velocity. If the shear wave velocity is way different it's probably disturbed. But just because the shear wave velocity is the same, I haven't proved it's perfectly undisturbed, because I could densify the soil slightly and break some cementation and get the same shear wave velocity. There's no way of proving perfection. So what you do is you do your best, and you just accept. What I've accepted is, for example here, if I'm looking at soils that have a tip resistance between 60 and 100 megapascals, I mean normalized, so it's 60 to 100 normalized tip resistance, in a clean sand, I get pretty consistent results. I have good indications I have not densified the material. For the denser soil, I get pretty consistent results in blue. For the loose, clean sand, it's all over the place. So I know the Dames and Moore hydraulic piston sampler causes disturbance in clean sands. But in silty sands and medium dense sands, it does okay. Have a good lunch. Actually, we're on schedule because we're supposed to stop at 12:10, but I know it takes about an hour and a half, so maybe the best thing to do is let's really try to get back here, including ourselves, by 13:30, and we can have some questions. You can talk amongst yourselves and go, I don't really believe this guy. I really don't understand what Professor Kramer is saying there. And we'll come back with some questions, and then we'll go forward from there. So 13:30.
¿Cuál es el último para ese día en
Aquí no lo creo, yo no creo que...
Vamos a comprar uno y que